Hello everyone, this is chapter 4, Descriptive Statistics. In this chapter, we talk about the numerical description of data, numbers, and statistics. We talk about central tendency, dispersion, standardized data, percentile, quartiles, and box plots. And in describing data numerically, there are three key characteristics of the numerical data. Right? First is central tendency, meaning where are the data values concentrated, what seems to be typical or middle data values. Right? The second is dispersion, how much variation is there in the data, how spread out are the data values, are there unusual values, extremely large or small. And then there is a shape. Are the data values distributed symmetrically, skewed, sharply skewed, flat, or bimodal, like we talked about last time? Okay. First, let's talk about central tendency. The first terminology we want to cover is mean. That's something you're quite familiar with. You should be familiar with, or it's also called the average. It's a very familiar measure of central tendency. The equation for that here is for the population, this is the equation. The letter Greek letter mu means the population mean, and the big sigma here means add up all the values in this data range from first one 1 to the last one n. The capital N stands for the number of observations in the population. Once you add up all the values, the individual values, you divide by total number of n, that's how many numbers you have, that will give you the population mean, or mu. And that's for the sample. Remember, a sample is a subset of the population. We draw a sample from the population. For the sample, we do not use mu. We use x bar right here. Okay? The sample mean x bar is calculated by adding all the xi's, individual observation number, from the first one, I equals 1, to the nth one, to lowercase n. And then with the sum, you divide that by n, the number of observations, you get your sample mean. Right? In Excel, you can use function average and the data range. That will give you the mean or average. Okay? That's the first measurement he used to calculate the central tendency. That's mean. The second one is called the median, that you probably have heard about as well. The median is the 50th percentile or midpoint of the sorted sample data. So to get the median, you need to first sort the data from low to high, and then you find the 50th percentile. You split them half in half, then find the midpoint. The median basically separates the upper and lower half of the sorted observations. If the number is even, let's say if number n is even, then you find the median, find the middle point. Then there are two halves, right? For the lower half and the upper half of the data. But then the median is then where there's no number in the middle. The median is the average of the middle two observations. There's no one in the middle, there are two middle ones. Right? You average the two to get the median of data range. If n is odd, that makes it easy. The median is simply the middle observation in the data array. For example, you have a data set with 5 numbers. The one in the middle is 5 is odd. The one in the middle is the third one. So that is your median. Okay? If you have 6 numbers, what do? You don't have a number in the middle. You have two middle ones, right? That's the number 4 and number 5. I'm sorry, number 3 and number 4. You can use 3 and 4, average the two, then you get a median. Then another way to measure central tendency is called the mode. The mode is simply the most frequently occurring data value. And you may have multiple modes or no mode, right? For example, the PE ratio, PE price earning ratios we talked about. Right? We can consider the following PE ratios for a random sample of 68 Standard & Poor's 500 stocks. The lowest one is 7. We rank order them from low to high. There are 2 8s, there are several 4s, 1 to 12, also 13s, some 14s, etc. The highest one is 91 right here. Right? Then, how do you find the mode? You find the one that is most frequently occurring. You know, which one is that? We can count. You know, there are 2 8, 4 10s, 1 12. There are 1, 2, 3, 4, 5, 6, 7 13s. Actually, that is the most frequent occurring ones. The others, none of them has 7 observations. In that case, the mode is 13. So for the PE ratios, we can also calculate everything, all the other tensor tendencies. The mean is 22.7206. How do you get that? You add up all 68 numbers and divide by 68, you get that. The median is 19. That's one in the middle. Right? And since it's 68, that's the average of the middle too. The mode is 13. As I said, that's the most frequently occurring one. The range is 84. How do we get 84? That is the lowest one, 7, and the highest one, the largest one is 91. The difference between 91 and 7 is 84. Okay. The sum is 1545. That's simply all the values added up, all 68 of them. The count is 68. That's because there are 68 companies. Right? To notice that if you divide 1545 by 68, what do you get? Exactly, you get a mean, 22.7206. Okay. Next, let's talk about the skewness. Basically, if you want to compare the mean and median and look at the histogram to determine the degree of skewness. If you look at the distribution is the left skewed left, that means the longer tail is to the left. You see there's a peak here, has to be the mode because that's most frequently occurring one. Right? The median should be somewhere to the left of the mode, so is the mean. Right? Why is the median over here, not on this side? It's because that's the one that separates the first half and second half. So there should be equal number of observations on either side. So since there are more numbers on this side, on tail side, therefore the median has to be on this side as well, because there are fewer numbers on this, or there are fewer numbers on this over here, but the over here, from this point on, you should have same number on both sides. Okay? When the data is distributed symmetrically, the mean, median, mode should be should all equal each other. They should be right here. Okay? When it's skewed to the right, or the longer tail is on the right, the mode is still here at the highest point. The median is on the right, should be on the right, so is the mean. Okay? That's skewness. Sometimes we do not use arithmetic mean. The means we normally use is called arithmetic mean, but sometimes we use geometric mean to calculate mean. Geometric mean, or G, is the multiplicative average. Basically, instead of adding them all together divided by total number of observations, we actually multiply them from x1 times x2 times x3 all the way to xn, and then we find the nth root. That's a geometric mean. And that's used in some of the growth rate calculations, like this GAD power quality data. Right? You find the quality data here, you multiply all 37 of them, divided by the find the root of 37th root of that, you get the number. A variation on geometric mean used to find the average growth rate for a time series. You know, the growth rate is actually calculated by geometric mean. You find the last number, observation xn, divided by the first one, x1 in the series, and the ratio of which you find the nth root of that minus 1 will give you the growth rate. Let's take to look at example here. For example here, from 2002 to 2006, JetBlue Airlines have the revenue numbers like this. In 2002, they made like $635 million. 2003, $998 million. 2004, $1.2 billion. 1.7 billion, 2.3 billion, right? Now, you can calculate the year-to-year growth rate. Now, what will be the average growth rate over the 5 years, right? Or the next 4 years, actually, from the base year of 2002. To calculate that, basically what you need is you use the last year, the year after, over the previous year. That's the 2003, 998, over 2002 value of 635. That's right here. And then for the following year, next year, you use 1265, 2004, over 998, the 2003 number. Again, 1701, 2005, over 2004, 1265. And then the last year, 2363, over 1701. Right? You can see that when you do that, 998 cancels each other. 1265 cancels each other. 1701 cancels each other. In the end, what you have is basically the last year, 2363, over the first year, 635. That's exactly what is said in the previous slide, right here. Okay. So basically, you find the ratio of 2363 over 635, and then you find the nth root. In this case, n is 4. That's 4 years after the first year. And that number here, the fourth root, is 1.3089 minus 1, you give you 0.389 or 38.9%. That is average growth rate in the last 4 years for this company. Okay. Yet another way to talk about central tendency is called the mid-range. The mid-range is the point halfway between the lowest and the highest value of x. It's easy to use but is sensitive to extreme data values. Excuse me. So let's say if the minimum is too small or the maximum one is too big, then this mid-range value could be skewed as well. For the J.D. Power quality data again, and the mid-range would be the lowest one plus the highest one divided by 2 gives you 147.5. Here the mid-range 147.5 is higher than the mean of 134.51 or the median of 132. Okay. Yet another way to describe central tendency is trimmed mean. Why do you use trimmed mean? Sometimes if we just use mean, we may find the extremely large number or extremely small number may skew the overall picture. Right? So then we can, what we can do is we can trim the data and then use the trimmed mean. Basically, to calculate the trimmed mean, we first remove the highest and lowest k% of the observations. The k could be any number you want. It could be like 1%, 2%, 5%, or 10%. Right? For example, for the n equals 68 PE ratios, if you want to have a 5% trimmed mean, that is k is 0.05, that's 5%. Then we need first to determine how many observations need to be trimmed. And we multiply k times n, the total number, 0.05 times 68, give us 3.4. Let's round it to 3. So we need to trim 3 observations from the top and bottom. Then we remove the 3 smallest one and the 3 largest observations before we average the remaining values. That will give us a 5% trimmed mean. So here's a summary of all the measures of central tendency for the PE ratios. The average, the mean is 22.72, right? And this is how you do that. You get it from using Excel, okay? And the median is 19. This is how you get it from Excel. And the mode is 13 from Excel here. And geometric mean is 19.85. Mid-range is 49. And trimmed mean, 5% trimmed means 21.1. You can see the mid-range is kind of like deviating from the other central tendency a lot, whereas the others are mean, median, and trimmed mean very consistent. Now let's talk about the dispersion of the data, or dispersion or variation. The variation is the spread of data points, about the center of the distribution in a sample. Let's consider the following measures of dispersion. The first one, measure of variation or dispersion, is range. The range is simply the largest value minus its lowest value. X maximum minus X minimum. In Excel, you can use the max data, the data range, minus the minimum, the data range. And the pro of this methodology, or this the concept, is that it's easy to calculate, but it's sensitive to extreme data values, as you can see. Another measure of variation is called sample variance. This is very important. It's denoted by S squared. We can use a lot of that from now on. Okay? This is defined by, you see, Xi is the individual observation minus X bar. If you remember, X bar is the average of all the observations. The difference is then squared, and then is summed with the sigma, big sigma. And then we divide that with n minus 1. Be careful, it's n minus 1. And this value here is sample variance, or VAR in Excel. This plays a key role in mathematical statistics, as you will see, but it's not very intuitive, in meaning. So what does it mean? It's not that obvious to ordinary eye, but that is very useful measurement. It's a concept here. And next one is called standard deviation, and that is also very extremely important one, and we use a lot extensively in the later chapters. If you look at the variance, the equation for formula for variance, remember that, right? Keep in mind this one. And then let's look at the standard deviation. What is the difference? You can see under the square root sign, that's exactly the variance. And we call the sample standard deviation S. Remember, the variance is called S squared. So S squared is the square root of S squared, of course, is S. In Excel, you can get that by equal STDEV, data range, you get standard deviation. Now this is the most common used measure. Use same unit as the raw data. If the raw data is the dollars, the standard deviation is dollars. When you take your first test, after you take your first test, when they give you the test results back, I'll let you know the lowest class score. I'm not going to tell the name, of course, the student's identity, but just give you the lowest number, lowest score, the highest score, the average score, and the standard deviation. Okay? And of course, also is not very intuitive in meaning. Yet another measure of variation is the coefficient of variation, or a CV. Now, CV is not the curriculum vitae, right? Not your resume. It's coefficient of variation. It's defined by S, the standard deviation, divided by its mean, the mean, and times 100, right? It measures relative variation in percent, so can compare data sets. Okay. Now, for yet another one is called the mean absolute deviation, or MAD, right? This is not the mutually assured destruction in the Cold War, right? It's just mean absolute deviation. How do we calculate that? It's basically Xi, each individual observation, minus mean, and then take the absolute value of that. Because if you use Xi minus X bar, you may get a positive number, you may get the negative number. You take the absolute value of that, then this is all positive. They're all positive. You divide that by n, that will give you the mean absolute deviation. You can do that with Excel as well, right? And for population, though, what we just talked about was for samples, right? For population, we use the sigma square for variance. This little sigma square, the population variance is xi minus mu, that's the mean of population, divided by n, that's capital N, the number of observations in the population, and that's some population variance. Please notice the difference between population variance and sample variance. The formulas are different. For population standard deviation, again, similarly, is the square root of this, the square root of variance. That's the same as sample. Okay. There is also a term called coefficient of variation that's useful for comparing variables measured in different units or with different means. It's a unit-free measure of dispersion. It's expressed as a percent of the mean. That is the S standard deviation over x bar times 100, the CV. Okay? It's only appropriate for non-negative data. It's undefined if the mean is 0 or negative. Let's talk about central tendency versus dispersion, right? The mean and variance, for example. In manufacturing, this is used to check for quality assurance and quality improvement. If you look at two machines, machine A and machine B, they both are supposed to drill a hole on the plate, the steel plate, for example. The diameter of the hole is supposed to be 5 millimeters. That's the desired mean, right? And what do you think about this one? There's one machine, right? And it looks like the average seems to be around 5.0, but there's too much of variations here, too widely spread, right? And it looks like it's old machine, it comes over and out, right? Machine B, look at that one. It seems to be more focused, more centered around, here the 4.998, and variation is acceptable, but the mean is less than 5 millimeter. Now this seems to be indicating that this machine B is a newer machine, but needs to be calibrated. If you calibrated, so the mean will move over to 5.0, that will be a good, better performing machine. Let's talk about the standardized data. There is a theorem called the Chebyshev theorem. Basically, this theorem says that for any population with a mean, mu, and standard deviation of sigma, the percentage of observation that lie within k standard deviation of the mean must be at least 100 times 1 minus 1 over k squared. Basically, if k equals 2, right, then for k equals 2, the standard deviation 1 minus 1 over 2 squared, there's a 1 minus 1 over 4, or 1 3/4 times 100 will give you 75%. Basically, this is saying that at least 75% of the observations will lie within 2 standard deviation of the mean. Okay? And then if the case 3 is 88.9, so or roughly 90% will lie within three standard deviations, right? And that's what the theory is about. We'll get to that later on. Basically, there's to be more generalized. There is an empirical rule. It says that for normal distribution is symmetric and also known as a bell-shaped curve, right? We can apply the empirical rule. The empirical rule states that for the data from a normal distribution, right, if the data follows a normal distribution, the bell curve, the famous bell curve, and then we expect that when k equals 1, about 68.26% of the observations will lie within 1 standard deviation of the mean. That mean the mu plus 1 standard deviation 1 sigma or minus 1 sigma. Between mu minus 1 sigma and mu plus 1 sigma, you will find 68.26% of data. Again, when the k equals 2, we expect to find between 2 standard deviation of the mean, we expect to find 95.44%. Within 3 standard deviation of the mean, we expect to find 99.73%. Now I want you to remember, calmly remember, have a good impression of 68%, 95%, and 99%, right? For mu's equals 1, 2, 3. We will talk about this in the following chapter as to why that is the case. Okay, just remember that for now. Okay, the empirical rule. This summarizes the empirical rule. The distance from the mean is measured in terms of number of standard deviations. This is the mu here is the mean, and 1 standard deviation is from plus 1 standard deviation, and minus 1 standard deviation is this range here. Basically, in this range, from this point up here to the curve, right, and back here and go down, in this area should cover 68% of the total, and the total area under the curve is 100%. Okay. If the 2 standard deviation from here, follow my cursor here, from minus 2, go up here, up the curve, go down to the 2 plus standard deviation, there should be 95% of the observations, the 95% of the area. 3 standard deviations, 3 sigma, you should have 99.73%. Now this is very useful. Okay. Unusual observations. We define unusual observations as one that are those that lie beyond the 2 sigma or 2 standard deviations. And outliers are the ones that lie beyond 3 standard deviations. So if I give you your test results back, I give you the average of the class, I give you the standard deviation. If your score is 2 sigma beyond, which is on the upper side of okay, if it's on the lower side, minus 2%, then you need to be careful, right? And you don't want to be falling outside of 3 standard deviation, 3 sigma. Then that will be an outlier. That will be too bad. Standardized data. Basically, what's standardized data? A standardized variable, or Z, redefines each observation in terms of number of standard deviations from the mean. The reason we find to standardize it, because even though for a data set or number, a group of observations that follows normal distribution, the normal distribution curve, the bell curve, could be skinny and tall or low and fat. In order for us to standardize, to use table to simplify the process of calculating, we need to standardize the variable. We standardize the data. Basically, how do you standardize it? The standardization formula for population is the z-score, we call the z-score, equals xi minus mu, that mean, divided by the standard deviation. Okay? Then the standardization formula for a sample will be xi minus x bar, the mean, divided by the standard deviation. Once you do this, you convert the number into a z-score, a standardized value. Then this follow a standardized normal distribution, which makes this much easier to calculate using standardized table, standard table. Yet another mean to calculate data, to find the described data, is by percentile and quartiles. Percentiles are the data that have been divided into 100 groups. For example, if you score in the 83rd percentile on the standardized test, such as SAT, that means 83% of test takers scored below you, and 17% above you. You can also divide the data into 10 groups. Then we call it the deciles. You divide it into 5 groups, we call it quintiles. You divide into 4 groups, we call it quartiles. Percentiles. Percentiles are used most often, as you can see. They're used to establish benchmarks for comparison purposes. For example, in healthcare, manufacturing, and banking industries, to use 5, 25, 50, 70, and 90 percentiles. Quartiles are used like 25, 50, and 70%, and commonly used to assess financial performance and stock portfolios. Percentiles are used in employee merit evaluation and salary benchmarking. Maybe your boss, your future boss, will give you a 3% increase in salaries. Another way to describe data, present data, is called the box plot. Box plots. It's a useful tool for exploratory data analysis, or EDA. It's also called the box and whisker plot. You'll see why in just a minute. Right? It's based on a 5-number summary. The 5 numbers are X min, that's the minimum number, minimum observation in the data series. Q1 is first quartile, Q2 is second quartile, Q3 is the third quartile, and then X max is the largest one. If we consider the P ratio, the 5-number summary of the P ratios, 68 observations, the X min is 7, Q1 is 14, Q2 is 19, Q3 26, X max is 91. Then with these 5 numbers, we can construct our box plot, or box and whisker plot. Okay? This is what the box plot is like. It's just like a box and a whisker. Okay? The box plot is displayed visually like this, and this shows the left end is the minimum, X minimum. The right end is X maximum, the maximum number. In the box, that's a whisker. On the box, this side is Q1. The middle here is Q2, and Q3 is here. The box plot shows central tendency. As you can see, this is all measure of central tendency here, and shows dispersion, and it shows the shape. This one is clearly kind of skewed to the left. Okay. There's another measurement or description, quantitative description of data. They call the mid-hinge. That's the average of the first and third quartiles, or Q1, Q3 averaged. And that's kind of like if you're on a box plot or a box and whisker plot, the mid-hinge is exactly between Q1, in the middle of Q1 and Q3, instead of Q2. Q2 could be over here, this side here, but mid-hinge is right in the middle. Because it's the middle, the name mid-hinge derives from the idea that if the box were folded in half, it will resemble a hinge, just like a hinge. That's why it's called mid-hinge. Okay. Now let's define a new terminology called correlation coefficient. Basically, we're not getting into details as to what this means and how to do a mathematical operation on that. Let's just show the definition of that. The sample correlation coefficient is a statistic that describes the degree of linearity between paired observations on 2 quantitative variables x, y. Basically, you have 2 variables, x and y. Let's say, for example, is the x is your income and y is your education. And we know for sure, education and income are correlated, meaning you have more education, your lifelong earning or income will be higher. And that's why you are all attending colleges here, right? And then correlation coefficient, or degree of linearity, we use R for correlation coefficient, is defined as this over that. In the numerator, basically you have is xi minus x bar, the individual x value minus its mean, and then times yi minus y bar, the other y variable. The product of 2 is summed from first one to the last one. That's in the numerator. In the denominator, you have 2 square roots here. The first one is x1 minus xi minus x bar squared, then summed. Second one is yi minus y bar summed, squared and summed, and then square rooted. Both square rooted, you multiply the square roots, and that's your numerator, denominator. And R is the ratio of the two. By definition, we're not going into the details here. The R mathematically cannot be larger than 1 or cannot be less than -1. So its value is between 1 and -1. It could be 0. Okay? Now, what's the meaning of that? Basically, this is what it is. Remember the correlation, the chart we talked about before? If when in the case is a strong positive correlation, R tends to be positive as well, the positive number, and it's close to 1.0. In this case, it's 0.9. When it's a strong negative, the R is negative as well, and also close to, in value, is close to -1. Right? When the correlation is kind of like a weak positive, the R is positive, but it's close to 0.5. When it's weak negative, the R is negative and also close to 0.5. When there's no correlation, there's then R is close to 0. When it's in this situation, we call it curvilinear, R is also 0, close to 0. But we see that there seems to be two trends here, kind of like a positive here and a negative, right? We get more into this about correlation in the regression, the last chapter, okay? So that concludes chapter 4, and we'll see you next time.